This is the Chapter 3 whiteboard lecture on silicate structural categories. This is going to cover PowerPoint slides number 49 to 70. In this lecture, we're going to cover the silicates mineral category. The silicates are the most abundant minerals in Earth's crust, and for that reason, we're going into them in a little more detail. We will be talking about many different silicate minerals. They are the minerals that we find that crystallize from magma, and so they create all of the igneous rocks. Just like other mineral categories, there is key elements here, and those are silicon and oxygen. So remember that key elements are those that occur in every example of a mineral in this category. So every mineral in the silicates category will contain silicon and oxygen. So why are they most abundant in the crust? It's because silicon and oxygen are two of the most abundant elements in the crust, and they easily bond together. All silicates include the silicates building block, which is referred to as the silicon-oxygen tetrahedron. The tetrahedron part is just the geometric name for the shape it takes, which is a three-sided pyramid. So we have triangles on all sides, including the base. This part of the figure, shows the oxygens, and those are the brown ones here, 4 of them, and the silicon, which is blue. And then the white bars are indicating the bond between the oxygen and the silicon. In reality, the structure looks more like this because the oxygen ions are much larger than the silicon ion. So you have those 4 oxygens and the silicon gets kind of nestled in the center. So if we have 4 oxygens and 1 silicon, and we add up those ionic charges, we end up with a -4 charge left over. So in order to build silicate minerals, we're going to need to add cations that will equal up to a +4 charge. So in addition to simply adding cations, there is another specific way in which silicate minerals build up their crystal structure, and that is through sharing oxygens. So if you look at this figure up here on the top, each one of the triangles is a silicon-oxygen tetrahedron. So each one of these is a building block of the silicates. And then the red and green spheres there are other positive ions that are linking, bonding all of those things together. In this case, each one of those triangles is separate from each other and being bonded together by some additional cation. But if you look at the figure right below it, you can see that we can link these tetrahedra together by sharing one oxygen between 2 tetrahedra. So that's a shared oxygen, that's a shared oxygen, etc. And then sometimes you can share more oxygens than that. So here we have a chain up here where we've got the shared oxygens. And then we've also got a second chain here with shared oxygens. But we're linking them together by sharing additional oxygens here. So we have 2 chains that are linked together. This is an important part of the silicate minerals as far as their structure goes, because it determines where the minerals will break most easily. So remember, cleavage is the identification characteristic that we use, and cleavage is how a mineral breaks. So the silicon-oxygen bonds are really strong. So it's very difficult to break across them. So if we look at this, let me use a different color here. If we look at this particular figure here, we would have a hard time breaking across these bonds like this. But if we had another chain here that was not actually bonded, so not sharing any oxygens, we could break right along there, parallel to the chains and between them. That would be a weaker area of bonds. And so you can see how that can actually control how a mineral will break. So we're going to go quickly through the silicate structural categories in a figure from your textbook. I'm going to focus mostly right on this column because we're going to go through each category separately in later slides. So this is just an illustration of the different ways in which they can share oxygens, these silicon-oxygen tetrahedra. And each way in which they can share has a special name. So for instance, these are individual or single tetrahedron. You'll see that we also call those island silicates. Then we have single chains and double chains, which are similar to what I just showed you on the previous slide. We can also have all of the bases of the tetrahedra linked together. So remember, it's a three-sided pyramid, so it's got a triangular base, and if you take every oxygen at that base, so this one and this one and this one are all being shared, that leaves this top oxygen that's pointing up that is still not being shared with another oxygen. Those are called sheet silicates. And then finally, if you do share even the top oxygen between the individual tetrahedra, then we have what's called a three-dimensional network or a framework silicate. So we're going to look at each one of these categories and learn one or two minerals in each of them. So the first one are the island silicates. So in island silicates, we have no shared oxygens. So that is this structure right here where we just have independent tetrahedra and there would be additional cations bonding these two together, but they're not sharing any of their oxygens with each other. The mineral we're learning in this category is the mineral olivine. We talked about olivine earlier in the slide on solid solutions because this is a mineral that sometimes has iron and sometimes has magnesium, and it can have a variety or a spectrum of those plus the silicate, SiO4, and that is that silicon oxygen tetrahedron. Olivine tends to be green in color. It can vary from dark green to lighter green. It has no cleavage, and that's because it doesn't have any shared oxygens. So essentially, all the planar faces of the crystal structure are equally weak or equally strong. So there's no preferred direction in which it will break. When that happens, we say the mineral is breaking by fracture, which is a more random break. Then we have single chain silicates. So here we're sharing oxygens just to create a single chain. And we could have another single chain over here, but they would not be sharing any oxygens between them. The mineral we're learning in this category is the mineral pyroxene. It also has a solid solution between iron and magnesium, and then it has its silicate portion over here. And notice that in olivine, the silicon to oxygen ratio was 1 to 4. And here we have a 2 to 6 ratio. We could simplify that as 1 to 3. And the reason that this is not 1 to 4 is because of that shared oxygen. So the color here tends to be dark green to black. And this mineral does have cleavage, which is controlled by those chains. The cleavage shows up as breaking at two planes that are at about 90 degrees to each other. So again, you cannot break this mineral easily across the chain, but you can break it on any side that's parallel to the chain. And that's going to give us those two planes at 90 degrees to each other. Next, we have the double chain silicates. In this case, we have linked the two chains together. So again, we'd have another two chains over here, which were linked, and another two chains over here, which were linked, but no linkage in between those. So in this, we're learning the mineral amphibole, and amphibole has a longer mineral formula. It has the silicon there, silicon and oxygen. It has calcium and it can have iron and magnesium. There are 5 spots for the iron and magnesium, but it's a solid solution. So we could have different proportions of iron and magnesium. Another component of this mineral is this OH group here. The OH group basically means that this mineral is hydrous. And hydrous means it contains water. It's not a droplet of water, but it is the components of water built into the crystal formula and the crystal structure. And that will become important when we start talking about melting things like igneous rocks and making lava. So this is the first hydrous mineral that we're encountering. The color is dark green to black, and it also has cleavage controlled by the planes that are between these double chains. Because it's a double chain, the 2 planes are now more like a diamond shape, where you have a 120 degree on one side and a 60 degree on the other side. Then we have the sheet silicates, where we are sharing all of the bases. So down here, all the bases are being shared, but not up here at the top. So in this case, we're going to learn 2 minerals, and they both fall into the group of micas. The minerals are biotite and muscovite. They both share one particular property, and that is a basal cleavage. And what that means is that they will break parallel to this base. Can't, and that's just one plane of cleavage. They'll only break easily and smoothly in that one direction. We're going to look specifically at some properties that are just specific to the specific minerals. So we have muscovite, often called the white mica and named for Moscow in Russia. So now notice in this formula we don't have any iron or magnesium. We have aluminum and silicon and oxygen and some potassium. And then this is another hydrous mineral because we have an OH group. So the lack of iron and magnesium is actually what makes this such a light colored mineral. So characteristic properties include the fact that it is light in color. If you get a thin enough piece, it actually looks clear or transparent. You can see through it. It tends to have kind of a silvery look to it. However, it is not silver. It doesn't, we wouldn't actually say this looks like silver, just silvery. The cleavage is controlled by those sheets, and you can see here how you can peel off a thin sheet because of that cleavage. And something that's specific to muscovite is that those sheets tend to be very flexible. So you can see how this in this figure, this one is kind of bent. Because of this property, muscovite actually used to be used in places where people could not afford window glass. So they would use pieces of muscovite in a window opening because it would at least let light in, even if they couldn't see clearly out of it, like you could with glass. But glass was expensive to make and very expensive to transport because it breaks so easily. So then we have not muscovite, then we have biotite. And the biotite mica is called the dark mica. It's much darker brown and black compared to muscovite, and that's because it has the iron and magnesium in it. Also has the water in it, so it's a hydrous mineral as well. So its cleavage is very similar to muscovite, except that when you break this, you find that the sheets are quite brittle. So they tend to break into much smaller pieces. They're not flexible like the muscovite is. Then we have framework silicates where all of the oxygens are being shared. In this case, we're going to cover one particular mineral and then a mineral group. So quartz is a framework silicate, or a three-dimensional framework, and the feldspar group contains three minerals that we're going to talk about that are also in this structure. So we're going to start out with quartz. The formula for quartz is SiO2. So if you think about it, you've got that silicon and then the bigger oxygens, right? We had 4 oxygens. So if you only have half, so this is the basic building block, if every one of these oxygens is shared between another tetrahedron, then you have 2 halves here, which is 1, and another 2 halves here, which is 2. So that gives you 2 to every 1 silicon. So when we're identifying quartz, colors are not characteristic, right? Not easily to use because quartz can occur in so many different colors. All it takes is a tiny bit of a trace element, and that trace element becomes the color of the mineral. This is because quartz with no trace elements is basically clear or transparent. It has no cleavage because when you're sharing all the oxygens, all of the bonds are equally strong. And so therefore there is no particular plane where it's weaker in its crystal structure and where it's going to break easily. These minerals are also harder than glass, so quartz is quite a hard mineral. Then we have the feldspar group. So again, this is part of the framework silicates. But in the feldspars, some silicon atoms in those oxygen silicon tetrahedra are replaced by aluminum atoms. That happens simply because the atoms fit in the same location and the mineral is growing from a liquid that has an abundance of aluminum. So there's more aluminum there, so some aluminum gets into that place where the silicon would normally be. But aluminum has only a 3 plus charge, whereas silicon had a 4 plus charge. So we're going to have to add some extra positive charges in order to actually balance out the charges and make a mineral. And that ends up creating the feldspar group. So the first feldspar we're learning is potassium feldspar, called that because K is the element potassium. So its formula includes 3 silicons and 8 oxygens. Normally it would be 4 to 8, but we have this one aluminum in here, and that aluminum has only a +3 charge, so we add the +1 charge from the potassium in to charge balance it. Adding this in changes the structure somewhat, so now we find that these minerals, the feldspars, do have some cleavage. So we have cleavage down here, 2 planes at almost right angles. The color of potassium feldspar is a very easy way to identify it. So color was pretty useless for identifying quartz, but here you can always count on this kind of orangish pink or salmon pink color. That will tell you have potassium feldspar. So the other 2 feldspars are a solid solution. They're a solid solution between sodium and calcium. But unfortunately, we cannot use parentheses to write these, and that's because while sodium is like potassium and has a +1 charge, calcium has a +2 charge. So for sodium, this formula is almost identical to the potassium feldspar. The only difference is sodium instead of potassium. But because calcium has a +2 charge, we actually need 2 aluminums and 2 silicons instead of this 3 to 1 ratio. So we're actually decreasing this by 2, right? Because we're substituting 2 +3s instead of 2 +4s. And so then we add up that extra charge, we make up that extra charge by the +2 charge of the calcium. These are pictures of plagioclase feldspar. It can range from kind of white to gray. It also has cleavage in two planes at about right angles. So those are the silicate minerals in their silicate structural categories. The other minerals we covered, we don't have separate structural categories for them, and you can find those listed, the minerals we're going to learn in each of those, in the PowerPoint.